Hi, and welcome to Unit 7, Day 2. This is the example video where we'll go over Step 1 for solving these stoichiometry problems. So before we begin, I just want to remind you that stoichiometry is a process by which we use mole ratios to convert from one thing to something different. So the key thing is that what you're starting with, you're given, will be something different from a different substance than what you're asked to find. Now, to do that, as I said, we're using mole ratios, and there are two types of mole ratios. One are the coefficients in the balanced chemical equation, and the other are the subscripts in a chemical formula. In this video, we're going to look at examples where we deal with subscripts in chemical formulas. Now, with that being said, if you did not watch the Unit 7 Day 1 video or pause it, you want to make sure you get that done before you do this. That way it will make more sense to you. Alright, so let's dive right in. So in each of these problems, what we're going to do is we're going to focus on the first step of solving these stoichiometry problems. Remember, there are two steps. The first step is to choose the correct conversion factor, and then the second step is to solve using dimensional analysis. We're just going to focus right now on choosing the correct conversion factor. So the process for that, of course, is reading and then identifying our given and find. And then once we do that, depending on what our plan is, we will either use the mole map if we have to convert from, we have the same substance, but we're trying to convert between different amounts. Or we'll use the mole ratio when we're trying to convert between different substances. And in this case, the amounts must be in moles. So we'll be going from the mole of one substance to the mole of a different substance. And also stoichiometry problems must include or involve a mole ratio. If it doesn't involve a mole ratio, it's not stoichiometry. So let's take a look at this first problem here. It says a cup of water has 15 moles of oxygen atoms. How many moles of hydrogen atoms does this cup of water have? And if it's helpful for you, there's a visual aid that you can sort of read through and understand like what exactly this problem is asking us to do. But we're going to focus really here on the skills for solving these problems. But these visual aids will sort of help you figure out what it's asking you to do. All right, so we've read the problem, and now we're going to identify our given. So the given would be 15 moles of oxygen, and it's important that you identify not just the value in the units, but included with the units the substance, because this is a stoichiometry problem, so you have to include that. So we're starting off with moles of oxygen atoms, and I know that because I have a number for that, and we're trying to find moles of hydrogen atoms. So in terms of my plan, I'm going from moles of oxygen atoms, I'll just put moles of O for that, to moles of hydrogen atoms. Okay. Now the reason why I put a big gap in between them is because I need to make sure that this, I don't really know at this point how many conversions I will need to do. I don't know if this will just be one conversion I can go straight through, or if I need to do different things. So let's take a look at where we're starting and what we're trying to find. So we're starting off with moles of oxygen, and we're trying to go to moles of hydrogen. Are these two the same substances? No. So this would be a case where we're having to convert between different substances. And the only way we can do that is if those different substances are in amounts of moles, in which they are. So we can do that directly. So actually this only is one conversion, because we can go from moles of oxygen to moles of hydrogen, and we do that using the mole ratio. So now we can go into our conversion factor now that we know our plan. In this case, we're going from moles of oxygen to moles of hydrogen, and it's in water, right? So since it's in water, we know, and I'll just write the chemical formula H2O, we're going to use the subscripts to sort of help us out. According to the subscripts, a mole of water has 2 moles of hydrogen and 1 mole of oxygen. It's a 2-to-1 ratio. So that means that 1 mole of oxygen, and again I get that from the invisible 1 as a subscript for oxygen, is equal to 2 moles of hydrogen. Okay, so this is the conversion factor I would use to solve that. All right, let's try the next problem. So the process is going to be the same. We're going to read it, identify our given and find, and then make our plan, and then figure out our conversion factor. All right, so this problem says how many grams of oxygen are there in 0.522 moles of water, H2O. Okay, so we are starting off with moles of water. And I know I'm starting off with moles of H2O because that's the value that has a unit. And notice once again, I don't just write moles, I write what the substance is. And I'm trying to get to grams, which means mass. So when you see grams, that tell you the mass. So the mass of oxygen. So again, I'm going to write it all the way at the end here, leave room because I don't know how many conversion factors. Okay, so let's take a look at these two substances. I have H2O and oxygen. Are they two the same things? No. Even though water has oxygen atoms in it, water and oxygen atoms are not the same substances. So if I need to convert from H2O to oxygen between different substances, they both must be in moles. So let's look at our given. Our given is in moles. I have moles of H2O, but our oxygen is in mass. So what I need to do is I need to do a conversion factor in between. I know I can go from moles of H2O to moles of oxygen. They're different and they're in the same, but they're both in moles, so that's okay. I can do that conversion. And then if I use my mole map, remember? So if I use my mole map, I can go from moles to mass, all right? So I can actually then just do one more conversion to go from moles to mass. So let's go ahead and write our map out our conversion factors here. So we'll start with the first conversion factor. When I want to go from moles of H2O to moles of O2, sorry, not moles of O2, moles of oxygen atoms. These are two different substances, so I would use mole ratio. Okay, so I'm going to use the mole ratio. Now the mole ratio is going to come from all these problems, it's going to come from the chemical formula. So in the case of comparing a molecule with its atom, we know that for 1 mole of water, so in 1 mole of water, we have just a mole of oxygen atom. So if we think about it this way, let me just write that down. You can think about it this way. In 1 water molecule, there's 1 oxygen atom. So in 1 mole of water molecules, there'll be 1 mole of oxygen atoms. So this is the conversion factor that we would use to go from moles of water to moles of O. All right, now we're going to do the next conversion, moles of oxygen to mass of oxygen. Now in this case, these are the same substances, oxygen, they're the same. It's just the amounts that are different. And that means it's a mole map problem. And you may actually remember this because we've done so many of these, but if you didn't, you have this as a tool. So we're going from our moles of oxygen to our mass. We do that by going through the molar mass. And remember the molar mass we would get from the periodic table. So for oxygen, the molar mass will be 16. So that means that 1 mole of oxygen is going to equal 16 grams of oxygen. So these are the two conversion factors I would use here. Okay, next one. 50 milliliter tank of CO2 at STP has how many moles of oxygen? So we're starting off with 50 milliliters of CO2. Now when you see milliliters, that tells you it's volume. So we're starting off with volume of CO2. And we're trying to get to moles of oxygen. I'm going to put moles of oxygen all the way at the end. Now, once again, I need to look at my given and my find. My given is CO2, my find is oxygen. Are these the same substances? No, they're different. So can I convert from volume of CO2 to moles of CO2? No. Remember, when they're different substances, both must be in moles in order to convert. Now right now my oxygen is in moles, but my CO2 is not. So my first step would be to get this into moles. So if I can get this from volume of CO2 to moles of CO2, then I can go from moles of CO2 to moles of oxygen. Remember, if they're different substances, they must be in moles in order for you to convert them. So this is the plan that I have. Okay, so now this plan looks good. Now how do I go from volume to moles, right? So that's my first conversion factor I need to work on, volume of CO2 to moles of CO2. Well, these are the same substances, just different amounts. This would be a mole map problem. Okay, so I'm going to go on my mole map, and I'm going from volume to moles. I'm going to use this conversion factor. 1 mole is equal to 22.4 liters. Now the next conversion I need to do is go from moles of CO2 to moles of oxygen. Now in this case, these are different substances. They're both in moles. This is a mole ratio. Now for the mole ratio, I would look at the subscripts in the chemical formula. So we're going to start with 1 mole of our molecule. The molecule is always in 1 mole. There's no subscript for a molecule, so you always set the molecule to 1 mole. And if you have 1 mole of CO2, that means you're going to have, according to the subscript, 2 moles of oxygen. 2 moles of oxygen atoms. Because it's just like saying if you have 1 CO2 molecule, you would have 2 oxygen atoms. Well, if you had 1 mole of CO2, then you would have 2 moles of oxygen. Okay. We've got one more to do. All right, so in this problem it says how many iron atoms are in 1 gram of Fe2O3. So let's figure out our given. We're given 1 gram of Fe2O3, which means we're given the mass of Fe2O3. And I want to know the number of iron atoms. Okay, so now I'm trying to get to number of Fe atoms. Okay. All right, so let's take a look at our given and our find. We're given Fe2O3. This is iron 3 oxide, and we're given iron atoms. Are these two the same things? No, they're not. Just because this has iron in it doesn't mean they're the same things. They're different substances. They have to be exactly the same. So can we convert from the mass of Fe2O3 to the number of Fe atoms? No, and why not? Because in order to convert from between 2 different substances, they both must be in moles. So the first thing I need to do is get them both in moles. If I can get the Fe2O3 into moles, so from the mass of it to its moles, so from mass to moles of Fe2O3, then I can go from moles of Fe2O3 to moles of Fe, moles of iron atoms, right? And then I can go from moles of iron atoms to moles of, to number of Fe atoms, okay? So this actually has 1, 2, 3 conversions that we need to do, okay? The middle part is the part where we use to convert from one substance to another. But in between that, we're starting off with mass of our given, and we're trying to find number of atoms of our find. So that means going into our conversion factors now. The first conversion factor we're going to look at is mass of Fe2O3 to moles of Fe2O3. These are the same substances. You're just converting from different amounts. So this is a mole map problem. Now for the mole map problem, you go to your mole map. If you want to go from mass to moles, so here we are at mass, we're trying to go to moles, we have to use the molar mass, which is what's on the periodic table there. Okay, so we would have to calculate the molar mass of iron 3 oxide, so 2 times 55.85 plus 3 times 616. That's how we would get the molar mass. And when I did that work and added them all together, I get the molar mass of Fe2O3. So 1 mole of Fe2O3 is equal to 157.90 grams. Just double check that. Sorry, 159.7. 159.7 grams. There you go. Okay, so that's my first conversion factor. Now I'm going to go from moles of Fe2O3 to moles of Fe. Now these are different substances. So when they're different substances, we're going to use mole ratios. And for all of these problems, our mole ratios come from the subscripts. So what will this one look like? Well, if we had 1 mole of our molecule is Fe2O3. In 1 mole of Fe2O3, look at the subscripts for iron, there will be 2 moles of Fe. So that 2 comes from the subscript. For the molecule, you always had it equal to 1 mole. All right, now we're going to do the last one, which is going from moles of Fe to number of Fe atoms. Now, in this case, when you're going from moles, the substance is the same, but you're just changing the amounts from moles to number of atoms. If we go to our mole map, we're starting at moles. We're trying to get to the number of particles, number of atoms in this case. We would use Avogadro's number. 1 mole is equal to Avogadro's number. So our last conversion factor, (6.02 times 10 to the 23). In this case, it will be atoms, iron atoms. Okay. All right, so that is it for this process. So what do you have to do now? Now what you're going to do is, there are some practice problems, and I don't want you to focus on solving it. I want you to focus on mapping out your plan and figuring out the conversion factors that you need, okay? So, and when you're done with this, on the last page of whatever page is listed on your document, but in your document, you'll have the answer key. I want you to check and correct your answers. That's super important that you check and correct the answers for these 5 practice problems. One last note, for the practice problems, it says question number 6. One of the problems is not a stoichiometry problem, but a mole conversion. Which problem is it and how do you know? Remember, in order for it to be a stoichiometry problem, it must involve a mole ratio, meaning you must be going from one substance to a different substance. So if in your problem you're not doing that, you're starting off with the same substance and ending with the same substance, you're just changing the amounts, it will not be a stoichiometry problem. All right, that's it for this video. Have a quality day.